Welcome to my experiment charge tapes for Physics 2 and the first lab of this semester. In this experiment, I prepared charged pieces of Scotch tape. After observing their interactions, I conducted an experiment to determine approximately how much excess charge is on one piece of clear charged tape. Briefly, the excess charge on each tape was found to be 1.4 times 10 to the 8 coulombs. The following experiment makes use of Newton's third law, as well as the models for weight given the experiment's proximity to the surface of the Earth, as well as that of electric force and electric field strength. Again, W equals mg was used as opposed to Newton's universal law of gravitation because of the experiment's proximity to the surface of the Earth. The reasoning behind each of the models will be further expanded on throughout the presentation. So the experimental procedure is as follows. It first involved making quote unquote base tape, making a handle on one of the tapes and sticking it to a table, and then making a charged or U tape. So a strip of Scotch tape around 20 cm long was placed down onto the base tape with one end folded onto a handle, and the U tape placed on top was ripped off in quick succession, charging the tape. It's notable here that two U-tapes here repelled each other, while a singular U-tape was seen to be attracted to a neutral object such as a book or a hand. In a brief tangent to answer the questions on the PDF, if a U-tape were to be positively charged, it should repel a positively charged pen, and if it were negative, attract. As previously shown, it would be attracted to a neutrally charged object, and after observing its deflection from a positively charged object rubbed on clothing, it can be concluded that the U-tape is positively charged. Finally, after two U-tapes were procured, one tape was placed as shown on top of two objects, and another tape was held below but not touching the B tape. And this led to the upper U-tape being observed to be deflected upwards. So before I discuss the computational model used, in this experiment, each tape is thought to have an equal charge and modeled to be a single point charge whose charge is entirely concentrated at a theoretical point at its center. Moreover, outside forces such as air resistance are completely ignored for the purposes of this experiment, justifying my use of only the two aforementioned models for forces, electric force and gravitational force. This is reflected in the calculations for weight and electric force here, and further on the function, which defines the calculation for the electric field. As you can see, I first established the experimental constants to be used, as well as the physics constants. We have Coulomb's constant, the charge on one electron, or proton in this case, G, as well as the length of one atom. L defines the length of the tape used, M the mass, and D dist, the distance between the two tapes upon deflection, and W is the weight. Or, no, W is the width of the tape. Okay, so first we calculate weight and the electric fields, the electric force, as mentioned. And using Newton's third law, they're thought to be equal and opposite to each other. We then calculate Q, the charge on each piece of tape, which is, again, assumed to be equal, and then the electron number. We are assuming the tape to be a 2D sheet with a thickness of one atom to calculate the number of atoms within it. And it's also a pure element, in this case, i.e. consisting of one species of atom only. Each piece of tape is modeled as a point charge here and here, and the observation location is from the bottom tape, and from that we can calculate r hat, the direction vector, and r. And let's see the results. So the green vector symbolizes the electric force of tape 2 on tape 1, and the orange the gravitational force. As you can see below, the output, this electric force, and the charge on each tape, as mentioned before, is 1.4 times 10 to the minus 8. We calculated the number of deficient electrons from the charge on each tape and dividing by the charge of each electron. And we can now see that the model indeed reflects our assumption that the weight and the electric force are equal and opposite in this experiment. So needless to say, we had a lot of errors and assumptions. First of which being ruling out air resistance as a non-negligible factor and assuming the charge of each piece of tape to be equal. Moreover, the act of holding the tape could have removed some charge from it as well, and we treated the long piece of tape as though it was a point charge with all the charge concentrated at the center of the long tape. So to answer the first what if question, what if electrons were positively charged and protons negative? Positive and negative signs are a purely human convention, and our observations would be otherwise ineffective, since positive and negative signs are not inherent to the properties of electrons, but rather created by us to describe nature. And as for the second what if, touching the tapes, it's important not to do this because touching the tape effectively grounds them, as the human body is a conductor. Thank you for listening to my presentation.